Hello again and welcome back to my review of Advent of Code 2024 in ARM Assembly. This is day 7. Day 7 is a very interesting day because as we look at my emulator, we see a lot of digits. There's like 13 to 15 digits or something. There's a lot of digits. We're well into 64-bit territory. So we have to deal with 64-bit numbers. Let's have a look at the problem itself. So, we've come across the bridge. We need to repair the bridge, apparently. But some some elephants have stolen all the operators for calibrating our equations. So we have this list of values here. On the left-hand side, we've got a larger value usually. On the right-hand side, we are trying to get the value on the left using all the values on the right, all of them, and a combination of add or multiply operations. So if we take the first one, we go, well, we've only got two values, so we've only got two ways we could do it, 10 plus 19 or 10 times 19, right? For the second one, we could do 81 plus 40 plus 27, or 81 plus 40 times 27, or 81 times 40 times 27, or 84 times 40 plus 27, right? Those are all the combinations you can use. And we go down through that, right? And so you were working out how many we can resolve by, is there a way that we can do it? There could be more than one way of arranging, like doing the operations. We just need to find if there's one. We don't have to find all of them, just one. Right? Or find out that there's none. And then for the second part, we add one more operation to this, and that's concatenation, right? And seeing concatenation is an operator like plus or multiply. It could take place any part during this the sequence. So you could have like 81 times 40, and then the result of 81 times 40 concatenated with 27, right? So you've got to watch out for that, right? It could be anywhere that you get concatenations in there, and that comes as a problem in this assembly, ARM assembly. Now the thing is that there's really kind of two ways you can approach this problem. Two ways that you really approach it. The first is to use arrays. You know what I should do? I should grab my... Oh, I got the wrong thing again. Oh well, let's get rid of these. And I'll bring it back again. Our paint. I'll bring back our paint. Let's put it on screen. And I'll show again, like sort of two ways of approaching this. Put it on. Got it there. Okay. So there's two ways you can sort of approach this, right? The first is to have something like a this will be good. This should be fine. I'll go for the brush here, right? You have something like a list, right, of all your numbers, right? So you might come in here like 28 is the first number. Like you've got all your numbers. I'll just put like a bunch of numbers in here, right? These are all the numbers that are on the left hand side. 28 on the right hand side, right? And so then you have your loop where you start in with a list. That's a pretty bad list. I shouldn't do this with the that doesn't work, does it? Let's do. You start in with your first number, 28, right? We'll just say 28, right? And then you build a second list at the bottom here, and you do each of the operators you can. So you've got 28, you do plus 10, right? And so you'd have 38 would be your next list out, and you'd have 280 because you multiply it by 10, right? And so that's the first iteration, the first time through the loop. The second time through the loop, you're doing 17. So you come back. Let's grab this. Let's move it up here. Right. Now I've got a blank space. Let's fill that in with some that work. Of course it doesn't work. That in white. Alright. And so the next one, we've got 38 as our starting one. Right. And so now we do like 38 plus 17, which is going to give us, what's that? Not that thing. I just want to check it out. Like 55. Right. 55. Then we've got 38 times 17. I got to like 646. And then you got 280 plus 17, which is going to be like 297. And 280 times 17, right? 280 times 17. 46760. And if you keep going through the loop, right, you move that bottom list to as the input for the next list, for the next round in the loop, and you do all the operations on for the next number on all the numbers in that list. And what you can do is that you can cull this list, any results that go above your target, you can cull those out to cut down the number of operations you're doing. But you go through this loop the number of times that you have numbers in your list on the right hand side, right? Which I think in this case goes up to about 12. Right? So this is it's not memory efficient because you can end up with quite a large number of numbers in these lists, but it is fairly time efficient, right? It's fairly time efficient. Now, although you're basically going to do the maximum number of calculations, so it's not the most time efficient, and it's also not the most memory efficient. It's quite memory wasteful, but it's simple to write, and on a modern PC that has multiple megabytes of memory, it runs pretty quickly. Right. The second option is to do recursion. Right, recursion. So in that case, let's say you got 27, 10, 17 again, right? You have a function where in this function you'll first do like 27 plus 10, and then it will jump out to the same function that will try to do 37 plus 17, right? And if that's doesn't get you the result, you're at the end of the list and it's not your final result, it'll fall back, and then it'll do 27, 20. Let's do 27 times 10, and then it'll go through here and do 27 plus 17. But actually it would try and do, over here would do times 17 as well, 37 times 17. If that wasn't the result, it would come back, right, and do 27 times 10, and then do 270 times 17. And if you have a longer list, you just keep going, the depth just keeps going on and on, down. Now, this has an advantage because the memory usage is way lower. Basically nothing, right? You just have to know your state for each level that you're at in this recursion. You've got your list, you still have your list, you have the value, like your present value. The memory is very low. And you do have the benefit that is if you hit a valid result, or you've worked out that, you've ruled out all other possible operations, you can end out without doing like every possible calculation. You can jump out. So you can save time, it's a bit faster, and memory usage is lower, but it's conceptually a bit harder to write. So those are our sort of two ways of like handling this. Let's have a look at what I've actually coded today. Let's look at the code. So what have we got? I've got my addresses again, the result addresses. I've got ASCII numbers here. I've got this new thing over here called left dec, which is the left side decimal in decimal representation, BDC representation. I'm deleting things again. Let's go there. Yep. We've got left B, which is in a binary, the left side in a binary decimal representation. That's going to be used for checking if I've reached the target result. We've got a value array. This is the array of the right side values in binary representation. BDC num. I'm not sure if I actually use this, but I've got it here anyway. We'll see. BCD, right? The binary coded decimal. One con, which is one side of the concatenation. And we've got ASCII lens. Now this one here is something I added very late optimization, which has the length of the characters, of the length of the numbers in, right, I should get this right, the lengths of the numbers on the right hand side, right? I'll show this off again actually. Let's bring this back for a second, right? So the lengths of these numbers on the right hand side, right? So for example, it would say 2, 1, 2, 1, 1, 1, 1, 1, 1, 1, 2, 2, 2, 2, 2, 1, 2, 1, 1, 2, 2, right? Has those lengths. And we'll see why that's important later. Alright, so let's go into our thing. We're solving day, right? We've got our normal pointers for reading out the input and the end of the input. We move R1 goes into 0. We load R. We store that into ASCII num. We clear out ASCII num. We clear out the pointer for the value array. We see we're using a W here. Word for the value array. So that's 2 bytes instead of 4, or instead of 1, which is this one here is strb is 1 byte. strw is 2 bytes, I believe. Go into our read loop, right? We compare, see if we're at the end of the input. If we're greater than, we jump to finish day. That's alright. We load in the bytes. We compare to OA. If it's an OA, which is the end of a line, then we go to branch convert val. If it's a 20, which is a space, branch to convert val. If we are x3, 3a is a colon, and that's, we've finished reading the left hand side, so we'd branch to convert left, right? Otherwise we're loading in a number, we stick into ASCII num, right? We do the usual, load out the pointer. No, we load ASCII num, we load the pointer that's in ASCII num, we add 1 to it, we store the byte, and we store the new pointer, we increment the offset, and we branch back to the loop. Right. So convert left, we'll branch to get left bin, get left binary, then we add 1, and we branch to increase offset, we add 1 so that we skip the space after the colon. We'll look at that get left bin in a second. Convert val, which is the standard one, we just take the value out of ASCII num. We load the byte, right? We load the byte there, or wait, and we load the length of the value that's in ASCII num, right? Compare it to 0. If it is 0, then we're at the end of the input probably. Now we're deleting lines again. Right, we set up our multiplying to convert it into binary. Right, R7 is our output, 5 is our multiplier, R6 is our 10 multiplier. Right, we load in the byte, the furthest byte along the right hand side byte, the ones column, multiply it by the multiplier, which is 1. We add it to the result, R7, we multiply the multiplier, R5 by R6, so it becomes 10. We store the multiplier back into R5, subtract 1 from our pointer, and we go back to the loop, so it'll be 1 times 10 times 100 times 1000, right, as we go through. We move 2 into R5. Check what I'm actually doing here. I move the value of 2 into R5. We load val array. Right. Because, oh no, wait, so the W must be a 4. The word is 4 bytes before. So I probably could have just done SDR, I believe, yeah. So that was a mistake. The further up here where I had STRW, that should be 4, I believe. 4 bytes. I might want to check on that again, but I think it's 4 bytes. Because this H, I think, is half word, which is 2 bytes. Which is why I'm using a 2 multiplier here. So I load the value from val array. I don't know why I'm using a W for that val array and then an H down here. It's possible that I've just made a little mistake there and I'm writing, like I'm clearing out a little bit more than I need to, but that's fine. So load our H, load 2 bytes, we add 1 to it, we multiply it by 2, which gives us our spacing multiplier, right? So the first one will go into the memory address plus 2, the second one will go into the memory address plus 4, the third one will go into the memory address plus 6, right? So that the 2 bytes, we're storing 2 bytes consecutively. We store it. That gives us our offset into 4 here. Deleting lines again. To 4 here. And then we store it into the address val array location plus the offset of R4. And then we store the new pointer. R2 back into R3. Into the val array. Right, and then we branch to store ASCII. Alright. We branch to store ASCII. That seems odd because it, oh no, right. This will be the store ASCII here is branching to the store ASCII, the length, I believe. And then we compare to again. Then we compare if R0 is a 20. If it's a 20, then branch to inc offset. If it's not a 20, if it's not a space, then we're going to evaluate the lines. Right? We've reached the end of the line. We want to evaluate for. We want to evaluate the line. We want to look to see if we get results. Right? First, we branch to silver solver. Then we come. So set R0 here. This is R0 is going to decide if we find a solution or not. Right. So the thing is, for part 1, anything that solves for part 1 also solves for part 2. Right. If we get a result using just addition and multiplication in part 1, then of course we get a result in part 2. We don't have to do the concatenation stuff. It doesn't matter. You get a result regardless. It's just, you know, there's just one more operator we can use, but we don't have to use it. Right? So if we have a result for silver, if it comes back, R0 comes back as 1, then we don't branch into gold solver. If we get a result in silver, then we'll add it to gold as well. And then we prepare for the next line. We store that into back into R3, which is the value array. We clear out the value array pointer, and then we go back into it. Okay, so let's see what we're looking at. We've got store ASCII here. Let's have a look at store ASCII for a second. Very short thing here. We load this value for ASCII num, and then we load ASCII lens. Right, these are the pointers, and I just take that value out, and then I store it into ASCII lens. So what I effectively doing here, you might see, is that I'm using the same value from up here. So val array, when I store this pointer offset for val array, I make this pointer offset for val array, right? Add one to it, add one to it, and I store it into there. R2. We jump into this store ASCII, and this uses the exact same one, right, for ASCII lens. Right, so the first number, right, will have an offset of 1. This one has an offset of 1. Right. That way I don't have to work it out again. Don't really have to store another pointer. I just use the same pointer, the same values really. Right. They're the same offsets from val r as they do in ASCII lens. Right. And then we branch into this clean ASCII num, which I believe basically zeroes out the whole of ASCII num. Where let's go down to it. This one's kind of long. It's kind of long. Here we are. Right. So it clears out 16 bytes of ASCII num. Right. R2 becomes 0. R1 16. Restore into R8. I think this assumes R8 is ASCII num, right? Whatever you come into here with, whatever's R8, it's going to be storing 16 bytes of zeros into it, unless I delete those lines. So if I come back up here, I think I might be using it more than once. Actually, that's kind of weird because, oh no, wait, is it down in, yeah, see, so let's, excuse me, there we are. See, I load R8 as ASCII num there, right, which is fine. It's fine, I can do that, everything's fine. And so when I call clean ASCII num, R8 is pointing to ASCII num and not where we're loading out of the input. Alright, so where are we next? I believe I need to get to convert left. Where was convert left? We need to check on that. Where was convert left? I don't know where I left it. Let's see if I can find it, can we? Let's convert left, yeah. There it is. Oh, it's right there. Did I go straight over it? May have not gone straight over it. Get left bin. That was the thing I was looking for. So, in convert left, we go to get left bin. I should have gone for that one there. There we are. There we go. That's gone. It's actually relatively short because we branched to BCD to bin. Yay! Binary encode decimal to binary. Right. And then we will move 0 into R4. We'll load R8 into R8 left B, which is the binary value. And then we store the bottom half of this, because it could be, some of these go up to really big numbers. It could be a 64-bit number. We we store the bottom half of it into there with the offset of 0, and then we put 4 into the offset, and we store it into the top half, R5 and R6. Now I could be doing addition here. I really could have just added 4 to it, but who cares? Everything's fine. It's fine. Everything's fine. Situation normal. Back now. I should go back up. I think just up here, BCD bin is sitting right here. Yes. Now, one thing that I first did. This is my second chance, effectively. The second improvement, second chance. The first thing I did, right? Because usually I have a function to convert binary into binary encoded decimal for my results. And for this one, I thought, well, I also need to go backwards, right? Because I've got this ASCII representation of possibly a 64-bit number that I need to put into a binary number. So the first thing that came to mind was, well, how about I just do the double dabble, reverse double dabble, right? I just do a reverse double dabble to convert it into a binary format, right, from the ASCII format. And that's what I first put in. Right, I did all this, I did the whole solution, and it was fine for the first, like this, just doing silver, but when we get to doing the concatenations in gold, I have to do a lot of conversions. I do a lot of conversions from binary back into, or from binary encoded decimal into binary. And the result would take like 9 hours to run, 9+ hours to run the solution. And I couldn't do that on Game Boy batteries, on the batteries. So that was certainly not a workable solution. One of the first solutions, or one of the first optimizations I made was this, right? Getting rid of the double dabble, or getting rid of the reverse double dabble, effectively, right? So, and this is kind of a thing where you really have to test like your known way of doing things against other methods of doing it, just to make sure which one is more optimal. It might not be like if you wrote it out as a like how many times you think you're going to do loops, or big O notation, might not be obvious because your loop might be so like complicated that you don't realize it. But if you can just benchmark it and then try it against something else, because what I first thought is that, well, I could do like, I could keep that multiplication, multiplying each place by 10 going up, but then eventually I have to start considering 64-bit multiplication. And I don't know how that's going to scale compared to doing the reverse double dabble. And so I kept the reverse double dabble, but then when I did this, right, I just carried that multiplication all the way up to 64-bit multiplication. It turned out it was much faster. I'll see how much faster in a moment. I'll give you a small pointer at how I worked out how much faster it was. So we come in here, we learn the ASCII num value from the top, right? The length of ASCII num. We load that. Yep, we load that value into R9. Move R10 is our multiplier. R4 is our 10. R12 is our limiter. 9 for the maximum of 32-bit. Right? R12, 9. It's the 9 times we can multiply effectively. I believe. We've got R5 and R6, that's where our result is going to end up. We do the low side first, right? So, we load in the first value, the ones column, we multiply it by the multiplier, we add 1, we add it to the result, which is in the low, we add it to the low side of the result, which is in R5. Subtract 1 from R9. So we go for the tens column. If it's a 0, if we've, R from R9, so we're, how far we're in, we minus 1 from R9, which is our pointer, which is how long the input is. If it's now 0, then we've done the full value that was on the left hand, and we can exit out of this BCD to bin, right? Before we even get to the high side of the 64-bit multiplier. Otherwise, we subtract 1 from R12 as well. And if that is now a negative number, so then we then if that's a negative, branch NE, multiply NE. If it's a negative number, we multiply R10 by R4. Oh no, not equal, sorry, not equal. If it's not equal to 0, then we multiply our multiplier, R10, by our by 10. So 10, 1 times 10 equals 10, or 10 times 10 equals 100. 10 times 100 equals 1,000. Into R1, and then we move from R1 into back to R10, and if it's still not equal, or if it's not equal, like that subs S is the only time that the those statuses get set, so then we branch back up to this low mul, right? So eventually, if it's a 64-bit number, this will equal, subtract 1 from R12, it will equal 0. None of these will run, and will fall through into this one here. We're looping the high side. So if we make it here, we're doing if we make it here, we're doing umul. This ARM language, ARM7, has the ability to do 64-bit multiplication, which is great. It's not that difficult to actually do 64-bit multiplication manually, but this makes it a little bit easier. So we're in this high mul part, right? So R11 is now 0. So we multiply R4 by R11, and we store it into R1. So it's going to be 0 in there, right? 0, 4 times, 10 times 0 equals 0. I believe. Whatever I'm doing. Move that back into R11. We multiply. We 64-bit multiply R4 by R10. R4 by R10, and we store the result into R1, the low 32 bits into R0, and the high 32 bits into R1. We move R0 into R10. Then we add R1 to, R1 to R11, which seems to be kind of weird. And then, so R11 has, well, R11 has our high result, the high 32 bits. R10 has the low 32 bits from the first half of the multiplication. Right. Then we load R0. We load R0. Right, because we have to multiply the high side and the low side by the value that we're using, by 10 or whatever each time. Something weird. Don't worry about it. Oh wait, I think this is actually me moving along the value. Right. I think I remember now. Yeah, I think that's right. What I'm doing here, now that I remember it, is I'm moving along this this tens multiple, right? Because let's write it in here for a second, right? So if we think about it like this, I'm going to go like this on the 0, 0, 0, 0, 0, 0, 0, 0. That's like the low, that's the high side, right? But it's not a good representation of the way of doing it, but who cares? Say you're multiplying by, like the first time by 10, and then it's by like 100, right? You get up here, you get to like, you multiply it by that, then I have to move it along to the high side, and that's what I'm effectively doing in this first half of the loop here, right? Multiply it by 10, 100,000, 10,000, 100,000, million, 10 million, 100 million, and eventually you have to go up into the, well, I'm already going up in there, you're going up into the 64-bit, almost going, you're going to the 64-bit range for your multiple, right? So I need to have that multiple in a 64-bit value, and that's what I'm doing in this first half of the loop, right? I set the top half of the multiple to be 0, and then I multiply it by the multiple, because the next time through the loop, it will be a non-zero, and then I have to multiply the whole thing, something like that. It's something like that. Who cares? It works. I'm trying to remember how it actually works. My mind is not working particularly great right now, but that's okay. Because I have to 64-bit multiply the bottom half of it as well. Yes. But anyway, then I load, once I've set up that multiple, I load in the value that I'm going to be multiplying, and I multiply that value by the high side, no, the low side, I think. High side, low side, one of the sides. And then I store that into R3. And then I do a 64-bit multiply. Then I add the value from R1. It must be the high side that I do first. I multiply the high side first. Then I multiply the low side by 60. It's a 64-bit multiplier. Right. I think I kind of remember now. Because you have to multiply each side effectively by your multiple. They do the high by the... I have to multiply the top side by... wait a second. Now I sort of remember. I think now I sort of remember, right? Because what I'm doing here is I'm multiplying the low side by the low side of the multiple, right? The low side of the like this value here, right? The bottom 32 bits effectively. So I multiply the top 32 bits, and that's always going to be a 32-bit multiply. It's not going to go into 64-bit and end up like 996-bit result. So that stays in the top half as 32-bit multiplication, but then I have to do 64-bit multiplication for the bottom half. And if it overflows, like if you get a high side result, I have to add that to the high side as well. So it's complicated. Let's increase that as well, right? So, and we keep subtracting from R9, which was the length, and we branch back up to high mul so long as it's there, right? So it's kind of complicated. It's kind of complicated, right? You multiply the. I mean, don't think I have to do actually this 64-bit multiply here, because I'm not doing any like addition things, so that might not be necessary there. But the thing is, you multiply the top 32 bits by your multiple, and you store that, and then you multiply the bottom 32 bits by a multiple, and then you have to, by the bottom half of the multiple, and then you have to add the overflow of that into the top half, right? If it carries over. That sort of thing. And that's how you get your 32-bit. That's how I get my 64-bit value out, binary value out. Rather than doing a reverse double. Right, so let's have a quick look at this thing here. So this is my debugger for Messen. And this had a really nice feature down over here, where you can see the number of cycles that have elapsed since the last time you paused, right? Just do a quick unpause pause. You get 3 million cycles done in that time, right? 4 million. Right. Tells you how many cycles elapsed since you last hit a pause, last breakpoints, right? So set up a breakpoint on the BCD, the reverse BCD, beginning and end, and I ran it, and it took something like 50,000 cycles to do a reverse double. Now when I changed it to this new code, this code here, BCD to this code here, right, the reverse double went, wow, it went down to about 1,000 cycles. So it was about 50 times faster. And that optimization alone got my result, my solution, to solve in about 2 hours, which is how I first released the solution. I ran it, recorded it, 2-hour solution. Hooray. But there were other optimizations left to make. So let's get into the actual solution part, shall we? Let's get into the actual solution part. Where are we? Let's go. We're down into the silver solver now. So we're going into the actual solution. We've reached the end of a line. We're checking to see if we're going to see if we find a solution. Come to the silver solver. The first thing I do is that I move R13 into R12. R13 is like the stack pointer, and I'm putting that into R12 because I want to keep that stack pointer for later it's a special tool that will help us later. Then we want to set up our initial, because I'm going to do a recursive solver. We load the first value from val array, right? The first value that we're going to be either doing addition or multiplication on. I move into R2 the value of 2, because we'll start from the second. Oh, right. Load the pointer for the val array. We load the actual value, the first value from val array, into R5. R6 is 0. Now I'm going to be using R5 and R6 as a low half, high half of a 64-bit number again. I'm going to use that all through it. Now load into R7, R3, the initial value, the length of lens, the number of values, the length of vals, right? And I move R2, I put R1 into R2, I put 1 into R2, which means that I've loaded the first value out of there, probably. And then we branch into recurse. If we come out of recurse, I move R0. I move 0 into R0, right? So that when we exit the solver, it will tell us that that we did not find a solution, right? So how do we know when we have actually found a solution in Silver Solver? We'll get there very soon. So we come into recurse, right? This is our branch into recurse. We move 2 into R4 because this is going to be our multiple, like how far we're jumping along val array, because val array, each value in val array has 2 bytes. We add 1 to R2, so we're going to the next value. We multiply R2 by R4 to get, which position we're going to be loading the byte, the half word out of. We sort of move the present states of R5 and R6 into R0, R1, right? So that 64-bit value. Then we load the value from val array into R4. We do a 64-bit add, right? So we add R4 to R5, the low half, and then we set the status. So if there's an overflow, then we add with carry R6, R1. So we're sort of writing over R5, R6, right? We're overwriting R5, R6. Our 506 values are sitting here in R0, R1, so we can use them again. Add with carry R1 with 0, so it will only add 1. It will add 1 if the carry flag was set. Otherwise, it doesn't matter. We compare R2 to R7. R7 was, where was R7 set? R7 was set all the way back here, right? R7 was all the way back over here. You can see here that when we enter recurse, we back up R0 to R6. We're not changing R7. R7, we are relying on R7 staying the same. We're relying on R10 staying the same. We're working only with those 7 registers. Right, so R7, if it's equal, if R2 is equal to R7, we're working on the final value in val array, and so we want to check if we have equaled, if we've reached the we've got the same value as the target that was on the left hand side. If we come back from that, or when we come back from that, we check if we've gone over the value on the left-hand side. If we've gone over the value, right, which should come back here onto R11, I believe. If it's a 1, then we skip to multiple. Otherwise, we branch not equal to recurse, right? So we need to do this. Like, say we've got overcheck as 1, we still need to try multiplying, right? There's a reason why we still need to try multiplying, because if the last value in the array is a 1, and we add that, and it will go over, and it goes over the target result, there's the possibility that multiplying by 1 will not go over the target result. Right? You know, if you're trying to get to 121, you know, and you're on 121, and you add 1, you get 122, you've gone over. But if you multiply the 1, you're on 121, right? So, if we've gone over, we do have to try multiple. We jump to the multiple, right? If we haven't reached the final value, then we branch to recurse again, right? We just branch straight back to here, which will store back up the registers again into the stack and do this again, right? So what it's going to do is it's going to build this history in the stack of values when it enters recurse, doing all the additions until it gets to the end, the last value, right? And then it'll finally start going down over here to the skip mul, right? Skip to smul. Then we do a 64-bit multiplication here. We're multiplying the top half first, and then the bottom half, doing a 64-bit multiplying the umul, and then adding the value that comes out in the top half to R6, which is the bottom half. Then again we check if we're on the final value in the array. We go to silver check. Then we check if we are over the desired value. If we are, then we go to the skip to S end, silver end, which will take those values, the last values off the stack, and come back. So when we take those values off the stack, we'll effectively come back here, come out of one of these recurse, like this branch here, right? We'll come out of that branch, right? We'll come out of that branch and we'll multiply whatever value was, you know, whatever value was in the state of the stack at the time, right? The state of those registers at the time. And this is how the recursion is working, right? We're using the stack to store the states of the registers at each layer of the recursion. And it's just going back and forth, up and down that stack in those states. Okay. So how do we get our result? How do we get out of this? Well, if we hit the silver check here, which go down here, I only back up one thing here, the return address or something like that, link address, and so I get here, I load this value on the left byte, right, the binary of the left hand side. I load that, the left hand side, I compare it with R5. If it's not equal, then we exit the silver check. Then I add 4 so I can load the top half of it. Load the top half and compare it to R6. If it's not equal, then we exit the silver check. If it is equal, right, we want to load our result, the silver side, the silver result 1, and we add the value that's in R5 and we have to do 64-bit addition, right? So we load it to the bottom half, right, and we store it, and we've got that add with an S. So if it overflows, we'll store that overflow. We'll keep that overflow, and then we add it to the R6 to the top side, and we add with carry, right? So we if it overflowed, we add that extra 1 into the top side, and we store that, and then we do exactly the same thing for the gold half, right? Result 2. We enable our interrupt, and then we branch to, well, if exit solver is not there, it's fine. Then we branch here to exit solver. Last thing here, we load, we store 1 into R0. We store 1 into R0. We branch to exit solver, and you can see the comment there: jump out of solver, invalidate stack. We invalidate our stack, right? We could have a stack that's like 10 deep in returns of values, register values for that recursion, right? But as soon as I jump back to this exit solver here, it will load the stack pointer from when I entered this silver solver, and I'll just invalidate all of those layers of the stack. And that's how I get out immediately out of this this recursive loop thing. And I think the best way to think of this is probably a go-to. Go-to isn't really used that favorably in programming languages these days, but it is pretty much just a jump, unconditional. You can put a condition around it. Unconditional jump to a location in your program, and that's what I'm doing here. Like in the recursion, I just go to getting out of the recursion, right? And there's only one more thing that I want to check in here. This overcheck, right? We're checking the left, right? We're checking the binary again, left B. If I check the high side first, yeah, I'm checking the high side first, right? Move R10 4. We load the high side, and if we are high, this is a bug that I had, because I did greater than, but the greater than, less than comparators are signed, so they go up to, they're signed 32-bit, whereas the high ones are unsigned, and you want to use high-low for like a 64-bit number. Or else half of the values think they're negative when they're not. So you check the high side. If it's high, right? If it's greater than if R6 is greater than R9, it's higher than R9, then we've gone over the value that's in the left hand side, and it's invalid. So we'd go over it and we'd load 1 into R11. If it's I think what I've got basically doing at R10, R11 are sort of scratches. I can just use the R9 as scratches, right? Everything above R10 is either stays the same or it's stuff that I can just use for anything. So like R7 I leave the same, but R10, R9, R8, R9, R10, R11 I just use for whatever I want. Whatever suits the purpose at the time. and if it's low, if it's below the value in R6, if it's below the value in R9, R6 is below R9, then it's definitely not over, and so we jump to not over. If it's equal, like we've got to here, it's equal, then I have to check the low side, and if it's less than, or well, it's less than or equal to, I think this is ls is less than or equal to, less or same or something like that, then it's not over and we go back out. Yeah, but otherwise we've gone over and we have to say that's gone over. Okay, so that's the silver side. That's doing the silver solution. That gets us back there. So now we have to get to the gold side. We have to get to concatenation, right? So we go into the gold side. Here we go, gold silver. Basically the same setup, except we jump to gold recurse, right? And you can see our exit gold silver here. Same way we're getting out. We're invalidating the stack and pissing off. Same setup as silver, except we're going to BL concatenums. Right, we're doing concatenation first. We're going to try concatenate. And that should come back 5 and 6. Right, 5 and 6. So the concatenate nums, I'm going to talk about this first. Originally I did this using the double double, again the reverse double double and the normal double double, because the reverse double double I had to use that. I was using that to convert the values that were in R5 or 6 or R0 R1 into ASCII representation, so I could then append the ASCII representation of the value that I was trying to concatenate from the val nums, right? The thing on the right hand side. Let's show that again for a second, right? These values over here. So I could append those to the present value that I had by multiplying or adding or concatenating, and then double convert them back into binary representation, right? So I was doing reverse double and double, both of them at once. We've already learned that the reverse double took 50,000 cycles compared to expanding that tens multiplication, taking only like 1,000 cycles, right? So taking off that reverse double saved a lot of time in this section of the program, but it was still like 2 hours, 2 hour solution, way too long to be workable. Well, it was 2 hours was workable, but still a very long time, right? So there was one more trick up my sleeve, right? And I'm going to go straight to it. So concatenums, and this is where the ASCII lens comes along. So what we do here, there's another way to concatenate numbers without actually going to sort of like a string definition, and it's painfully obvious once you realize it. Like I realized it. I was talking to someone afterwards, after the fact, explaining the problem to them, and it just popped into my head how to do it properly. So let's say you have a number like, let's write this out. I have 2, 4, 7, 6, like 2,476, right? And I want to concatenate the number like 89 to it. Right, so how do I do that without converting to strings? Like, how do I do that without doing strings? There's something very, very easy you can do. If you can just make 2, 4, 7, 6, 0, 0 plus 89, then you concatenate the two numbers together that easily, right? So all you need to do is know the length, the ASCII length of this number on the right hand side, and then you multiply the left hand side, right, by like 10 to the power of that length, and then you add the right hand side to it. And that's how you can concatenate them together very quickly. Very, very quickly, very efficiently. So what I've done, I've got those ASCII lens, right? I've got those ASCII lens. They are all in the same positions as the ASCII numbers themselves, so I can load out the length using R2. Here I've got a multiple 10. R10 starts at 1, right? So it's going to multiply by 1 first, I think. What's going on in here? There could be something fishy going on in here. Anyway. So I multiply... Right. No, I think we're okay. I think I've just got this little weird thing here. That's alright. Right, so I've got to get the length of it, and I've probably done this kind of a stupid thing. Load out the length, which is R7. So I multiply. So I multiply 1 by 10 the first time through this loop, right? And then I move that back into R10, subtract 1 from R7, that length of the num. If it's not equal, we branch back up here, and I multiply it again. So it's, I'm going to multiply 1 by 10 at least one time. So one time for one length, one time for a right side number that's 1 in length. 2 times for one that's 2 in length. 3 times for one that's 3 in length, right? So for a value that's a number that's in the hundreds, it will multiply it 3 times. And then I multiply the value that's in R5, R6. Oh no, I multiply the value that's in R1, R0, R1 by this multiple that we've just made up here, in order to shift it along the number of places I need in order to add that right hand side, right? So multiply the top half, right? Multiply the R6, and then multiply the R5, and then add that result, that part, the high side, to the R6 side, and then we add the value in R4, which is our val array number, into R5 with the set the carry if we need to, and then we add the carry to R6. Could be a 0, could be 1, right? And we come back out. We've done the concatenation, right? And again, that was something doing the double dabble took about 50,000 CPU cycles, less than 1,000 now, right? Saved 50 times faster. And that was the second big optimization in this program. Then we've got gold checks. gold check, same as the silver check effectively, except I'm deleting values again. Same as the silver check, except that we'll only be adding to the gold result. Over check, exactly the same, right? It's not gold over check, it's just over check. If we're not over, we'll go into the gold multiply. Right. If we're equal in length, but we're not over and we're not the result, we go into the gold multiply. We jump down here into gold multiply. If we're not over, if we've not reached the end of the array, we go to the next step in the recursion, right? Then we have the gold multiply, same thing as the silver multiply. Do a 64-bit multiplication, right? Do the check. If we've reached the end, we do the check. We check if we've gone over. To exit out. If we go otherwise, to go into the skip to gadd, right? The recursion thing there, and we do the addition if we need to, right? With the over checks and skipping to gend if we need to, and otherwise, no. If we're not at the end, we go to the next step in the recursion, and then we exit out if we need to. Undo that. We exit this level of the recursion if we need to. A gold check, right? Same as the silver check, but we're just doing the gold side, adding to the result. Step 2 result. Enabling interrupt if we've got a result. We branch to exit gold solver, which is our invalidation of the stack, and jump out. And that is everything. Finally, we are an hour and 10 minutes, and that is now everything. We are fully done. And I think, where are we? And I think this BCD num is not used. And I think the one con is not used even. So yeah, a bunch of things got deleted. So it's time to run. It is time to run our result. Let's have a look. Got messen here going. It is running. I left it running apparently. Let's get our memory viewer up as well. That's not the memory viewer. This one here is the memory viewer. Okay, let's have a look at the memory viewer as well. This will take a little while to run. I'll run it once. I don't know. Am I on the internal work RAM or the external work RAM here? I can't remember. I think it's internal. Wait, let's think. Internal. Yep, we're completely on the internal work RAM. All right. Ready, set, go. And it's off. It's going nuts. You see, we've got some big values in there already. Down here, we've got the lengths of those values in the val array. What's going on up here? I think this one here is our left side value. Here is the number of the val array. And see, most of the time it's stuck here with OC, which is 12. You got 12 values in the val array, and it's it takes the longest to get through them. Sometimes you see 8 or 9 in there, or a B in there. All the ones that are lower than that pretty much solve instantly, right? And so you see the difference of having like 3 concatenation or 3 operands, right? Is it exponential? It's probably worse than exponential. It's probably cubed in the amount of time it takes to go through the all the possibilities in these lists, right? So you've got all the val arrays there. These are just the results, result 1, result 2. Right, you can see the decimal side here. I'm using a full like 16 characters, 16 bytes for each one. The gold result down there. And how are we doing? Unfortunately, I can't really see how I'm doing, like how far we are through. But what I can do is that I can bring up the browser again. Is the browser on top? No, it's on top. Yes. No, it's on underneath. There we go. And we can have a look where our results are. Okay, let's see. Can I see both the results? Not quite. Let's move this up just a little bit over there. And it should be going. How are we doing on here? This here is taking up too much space. Where are we? A little bit smaller, shall we? Dunk. How are we doing? We're getting there. We're getting there. I think it takes about 4 minutes. If I remember correctly, we get a very big one near the end. For the see, the silver's getting pretty close. Silver's almost there. Which means the gold one, yep, we got like another, I don't know what that is. What is that? Thousands, millions, billions, trillion. We got like 50 trillion just a second ago. And we've got like, oh, we're almost there. Almost there. Under a trillion left. Just a little bit to go. It should say done at the bottom when we are done. There we are. There's our result. It's complete. So as you can see over here, our result 1545311493300. That's correct. And our gold result 169, nice, 1221127165771. It's correct, right? So that was day 7. That was a hell of a day. That took quite a long time to complete. And I think in a lot of ways, I think that one, this day 7 is the most impressive. It's the most impressive out of the days that I've completed in ARM assembly. Alright, but we've got some cool days coming up anyway. Day 8 and day 9 should be pretty good as well. And then we've got day 10. Day 10 is the last one. Okay, thank you for coming again. This one's been a long one. I hope it was somewhat enjoyable. I hope you learned something. And I hope you'll be back for day 8. See you then.